Dr. Jens Küchenmeister. He studied physics, mathematics, followed up with a PhD in theoretical physics, focusing on light propagation and photonic nanostructures. And at Thorles, yes, please come on stage. Give him an applause. Come on, we get more, we get more, we get more. In Thorles, you are working on setting up teaching experiments and how that looks like. You let us know. Please, stage is yours.
Thanks so much. Good afternoon, everyone. The problem that I would like to address is one that I'm sure many companies here have. And the question is, how do we get a quantum-ready workforce? Right, because we have our well-trained experts, very few of them. We have students graduating from university, so we have to motivate them going into the field of quantum technologies. And we have a vast amount of smart but untrained engineers. And how do we excite them? And how do we teach them to go into the field of quantum technologies? And the answer that we have is our educational kits that we offer, because we have a very firm belief that while there are many nice educational offerings out there, you know, digital, there's nice games. In the end, the way to excite an engineer and the way to excite a student is to give them something in their hand. Put something on the table, let them see something, let them work with something in real life. And we do offer a couple of quantum kits, so this is the top row there, and in particular what I would like to show you today is our new quantum optics demonstration kit. So we do have a couple of kits so far, quantum eraser, bomb tester, more on the academic side. Then there's a setup which is quite nice about quantum cryptography. So everyone doing quantum key distribution, and you want to teach your employees or you want to teach whoever about quantum cryptography, how this actually works, you can get the setup over there, and you can really play through the entire BB84 protocol. It's not a quantum optics kit in that sense that it deals with single photons. You're just sending pulsed laser, but you can still go through all of those steps to teach about what quantum key distribution means in practice. But without further ado, I want to show you about what our quantum optics kit looks like. And so this is what you see here, and I will walk you through the optics and what you're seeing there. We're starting out with a 405 nanometer laser. We're going over 2 alignment mirrors. Then we're hitting a nonlinear crystal. This is where sort of the magic happens. What we're doing here is we're generating pairs of photons, and they are entangled. Now, once the blue laser has passed through the nonlinear crystal, we don't need it anymore, so we send it to this beam dump over there. And as I said, these photon pairs come from the nonlinear crystal, and we collect them by those single photon detectors at the top right. And as you may see, they have little noses there. There's basically just a lens there to collect the light and send it to the single photon detector. And for a couple of experiments, we send the light down with a beam splitter towards this Michelson interferometer on this black aluminum breadboard. And at the output of the interferometer, we have a third detector. Now, in order to do all the electronics, to do the data processing, we partnered with Swabian Instruments, that you may know. It's a company actually from Stuttgart who do very good time taggers. They have a very nice software package that you can easily integrate, and they made us an education-grade version. So cheaper, but worse timing resolution, but perfect for that experiment. And also, well, you need a couple of tools to get the system aligned. I will talk about that in a second. So the question is how to build a non-classical light source. And I just said that essentially just shine a laser on a crystal. If you're doing it right angle, right polarization, you get those photon pairs out, and you're creating those pairs, and you always have to measure those pairs. So that brings us to the question, how do I measure that? Well, we just had a talk about single photon detection, so we're placing 2 single photon detectors there. We have ones that are very, very small, so you can really easily integrate them into an experiment. And the whole point of those is that I need to make sure that I'm really counting those pairs. And I do that just by timing. So if detector T clicks and detector A clicks a nanosecond afterwards, well, it probably was the pair. If detector T makes a click and detector A makes a click like a millisecond afterwards. Then it was like stray light or a dark count, so we just discard this event. And so we're defining a certain coincidence window in the order of like 5 nanoseconds normally, and that really helps to get rid of a lot of the stray light and the environmental conditions. Now, that's the fundamental question. What is really non-classical light? How do I know that my light is a non-classical light source? Or the other way I could put that is, what's a photon? What's a single photon? And there's a famous quote by some Nobel Prize winner that you should actually do some sort of driver's license before you're allowed to use the word photon, because it's so complex and there's so much nuance to it. And it's really helpful to, picture that engineer that you want to excite about quantum optics, and you start talking about single photons and you start drawing little dots. That's quite problematic, right? There's not little dots flying around. So show him something, put something on the table, and this is what we're doing. So we're actually performing this experiment. You place a beam splitter into one of the arms, and now picture a single photon, right? A photon, by definition, you can't split that. So it will either transmit or reflect, not both, and that's the key. So essentially, you're just looking at the counts at detectors A and B, and if you find that they click not at the same time, then you don't have a classical light source. In contrast, if they click together quite often, then something's fishy. You can't have a single photon source. And so you pour all that into mathematics that looks fancy. It's called autocorrelation function of second order. It's not really fancy. You just plug in all those different count rates from the detectors. And in the end, you get a number as a result. It's really just a number. If it's 1, then you deal with coherent light, essentially a laser. If it's larger than 1, it's classical. And if it's smaller than 1, then you're in the non-classical regime. And then it makes, actually, that's the point where it starts making sense to talk about single photons. And in our experiment, we get well below 0.1, so we can say, yeah, we're really dealing with quantum optics. Now, let me take you into the experiment itself. One of the ones I enjoyed the most is the single photon Michelson interferometer. So now we've built our source, we aligned it, and now we're adding another beam splitter, 2 mirrors. We place one on a moving stage, and that's how it looks then. So on the left-hand side here, you have the stage with a mirror, you have your beam splitter, and your mirror down there. And that's the software that comes with the kit, so you don't have to write anything yourself. There's 2 plots, equally important. The top one shows you the coincidence counts between detectors T and B. So again, you have to count the pairs. We're counting one of the photons at T, we're counting the other one at B. We're moving the mirror, and you're seeing this interference pattern that you would expect from a Michelson. But the funky physics actually is the green curve at the bottom, because at the same time we're always measuring this autocorrelation function of second order, and as I hope you can see, we're well below this classical limit of 1. So those 2 curves together form the proof that single photons show interference, even a single photon. And I know that most of you are experts. It's not like I'm surprising you by that result. But if you're asking someone, even physics professors, have you seen that experiment in real life? 95% are going to say no. And that's the whole point. Give them something to work with, put something on their table. And this is why we made this kit. Few words on the alignment. If you don't have to be a quantum optics expert to put this into operation. So we have a very detailed manual, and we have a very thought out alignment procedure. And what we do here is we take a so-called axicon, which is essentially just a cone of glass. When you shine a laser beam on it, what you get is a cone of light. And as you can see here, this is not Photoshop, this is an actual photo. You see this laser ring, and if you're moving the screen further away, it gets larger. If you're moving it closer, it gets smaller. And the point is that the opening angle is tailored such that it matches the opening angle of the photon pairs coming from the nonlinear crystal. And this is the way that we align the entire system. It's really reliable. And so if you have to put it in operation yourself, you don't have to be an expert. Yeah, there's a lot of other experiments, obviously, in the kit. So you can spend a lot of time there, a lot of learning opportunities. two most important things I would like to mention is the quantum eraser experiment and also the fact that attenuated lasers are not single photon sources. So this is one of the most common misperceptions when you have your laser beam and you picture it like a stream of photons and you start attenuating, then, well, in this naive picture you would say, eventually I'm going to be left with one. Don't I have a single photon source? And as most of you know, that's not the case, but you only know it until you've actually verified it experimentally. And this is what you can do in the kit, and you can really show, okay, you really need something more fancy than an attenuated laser. There's much more. One notable addition that I would like to mention is we can actually turn this into a really, really simple quantum computer. And obviously we can't do fancy stuff with it. It's really the simplest algorithm you can think about, which is Deutsch algorithm. And the only thing you need to change is you have to put in two liquid crystal wave plates in the interferometer. We explained that in detail in the manual. The kits are not the parts are not included in the kit, but it's not too expensive. And again, the whole point is not to have something that factorizes 21, right? The point is to have something on your table to actually talk about qubits, to say, okay, this is a literal 2-qubit system on your desk. It's single photon 2-qubit. You can do the simplest operation you can think about, but you have a quantum computer on your desk. No cryo, no whatever. It just stands there. So that's the cool part. It just gives you an opportunity to talk about this without just having a 10-hour PowerPoint presentation. Okay, and the way that you can do is, you have these quantum circuits. I'm not going to go into detail here, but the point is you can translate that to the optical domain. So down here you see an interferometer type, and we can go one step further and identify the necessary parts in our setup there. And then as an end result, you get the plot at the top left, which is essentially like a logic 1 and 0. And you can see, yeah, that's what you should see. And there's, of course, a lot more to it. You can just read it in our manual. At the top right, you see it. It's free for download, 150 pages, a lot of theory, a lot of photos, how to do the alignment right. Price is obviously always a question. This kit clocks in at 30,000, but it's just the sum of the components. So we don't add anything for R&D. It's literally just the sum of the components. And the value for money that you get for that, I think, is quite good. Finally, I'm going to be here. We have a booth at the wall right over there. Thor Labs is not just a company doing educational kits. Actually, we're doing so much more. Actually, Thor Labs, if you don't know us, we're one of the largest optics and photonics manufacturers. And we're doing a lot in the quantum world as well. For example, you can buy finished photon pair sources from us. Detectors, single photon detectors, like super low noise laser systems. And then there's standard stuff like very, very stable optomechanics, fiber components, and so on. So if you want to, just meet me over there at our booth.
Yes, thank you so much. And I think, Jens, I'm sorry, we're running a little bit behind time. So if it's okay, I would recommend everyone that they actually meet you at the booth.
Gotcha.
I love that setup. And everyone who wants to follow up, you said, where is your booth?
Right over there.
Okay, right over there. Thank you so much, Jens.
You're welcome.